Hello everyone. Today we are going to start discussion of this extremely important problem of plate with a circular hole under uniaxial tensile loading. In fact, this is one of the most important problems in all of applied elasticity, and uh, to be sure, we must emphasize that it doesn't get any more applied than this. The reason is, in many different mechanical engineering situations, you will find that the situation can very well be modeled either directly by this kind of a problem situation or some variant of it. Furthermore, uh, another variant of this problem, which does not actually involve this type of a circular hole but an elliptical hole, is actually the gateway to a completely new branch of mechanics, which is referred to as fracture mechanics. But of course, we won't have the time and scope to go into all of that, but it is extremely important point to note that that entire discussion of fracture mechanics has its groundwork sort of in this problem. Okay, so with this motivation of addressing this very important problem, let us get down to how we may address the solution of this. So we have this apparently not very convenient looking situation where even though the geometry is very regular, like we have a rectangular plate, it's a nice geometry, and within it very nicely there is a circular hole. But if you think about how we may address this elasticity problem in terms of finding out the stresses, there does not seem to be a direct way out. Okay, so suppose this hole were not present, then this is a very easy problem. We have all done this. Like it's a direct application of a second degree polynomial. But the presence of this hole makes it a very challenging and very interesting problem. So how do we address this? All right. So we start out with the situation of what we actually know. Okay, so what we know is the solution to the very simple problem of a rectangular plate which does not have a hole. So let's start with that point. Suppose, let's imagine that this hole is really not present. What we'll do then? So if the hole, okay, so if the hole is not present, so if, let me just change the pen style. So if the hole is not present, okay, so we imagine such a situation. If the hole is not present, then the solution is easily given by this kind of an eddy stress function. So phi is equal to s y squared. So what is s? S is nothing but the magnitude of this uniaxial tensile loading. Okay, so we have s here, s on this side is nicely balanced, and this y, you please note, is simply it's simply the y-axis like this. So we have the corresponding x-axis on this side. So this is our x and this is our y. And you may be thinking that we were discussing 2D elasticity under polar coordinates. Why have we reverted back to this xy system? So it's not like that. So we'll soon be converting this, like in the very next step, we'll be converting this to the polar coordinate system. So if you do that, okay, so we know that y is equal to r sine theta in the corresponding polar coordinate system. So this is absolutely equivalent to s r square sine square theta. All right. Now, please note that the motivation of writing it like this is to actually obtain the solution that sigma xx is equal to del square phi del y square is equal to s. Okay, and please note that in order to get this thing adjusted, I must put a half here. because after the differentiation, after the first differentiation of phi with respect to y, I'll get this twice out, so that must cancel with this half, and when I do the second differentiation, I'll ultimately obtain s. So sigma xx is actually s. So all that is fine, and please let us not forget that this we are imagining under a situation where the whole is not present, so we have to ultimately bring back the whole, but that is for later. For now, what we are really interested in obtaining uh, is after convincing ourselves that this kind of an airy stress function does actually give us the sigma xx, we know this very well. What are the forms of the corresponding stresses or the stress components in the polar coordinate system? So what are the expressions of sigma rr, sigma theta theta, and sigma r theta corresponding to this half SR square sine square theta? So let's get back to our Jupyter notebook and see what those expressions are, and that those expressions will actually give us some clue as to how to address this problem of plate with a circular hole. Okay, and please note, okay, so this problem can actually be solved by the way that we are going to solve it only and only if this kind of a circular hole is not too large. Okay, it needs to be very, very small. Okay, so let's go to Jupyter notebook and find out the expressions of the stress components in the polar coordinate system. So I have already fired up a file here. So as usual, we'll import our polar utilities, everything from polar utilities. This will take a little moment. All right, we are done now. So the first thing we'll set up is the symbol S, because that is the magnitude of the applied tensile loading. With that out of our way, we can actually define our airy stress function in this fashion. Now, you please note, let's take a quick look back. So you note that this is phi is equal to half of sy square. Now, we might be initially tempted to write this or to instruct in a codified form to write this as 0.5 or 1 by 2 sy square. But remember that we really want to do this in as symbolic a fashion as possible, and there is a way to write this in a proper rational fraction kind of fashion by this way. Okay, so we won't write this as simply 1 by 2 or 0.5, rather we will define this half like a proper rational fraction, and the way to do it is by this command, sim.rational 1 comma 2. So suppose we wanted to write this as 1/3, then we would simply have to write this as sim.rational 1 comma 3, and so on and so forth. All right, so what we really want to write is half s into r square into sine square theta. Please note that I do not have to specify or define the symbols r and theta, because those are already defined in my polar utilities package. Okay, so if I want to display my phi, I can do that in a nice fashion. I just have to use the display facilities from IPython. It involves a little bit of more typing, as we have seen many times earlier, but the end result is quite neat. So let's do that. All right, so that's how it is. So phi is equal to half of SR square sine square theta. Now corresponding to this, what is the sigma RR? So we use these function definitions, sigma underscore RR, which is actually the function name defined within the polar utilities package. Similarly for sigma theta theta and sigma r theta. And again, we display this in a nice fashion. quickly copy paste the remaining two to reduce the time involved in typing. So that's my sigma theta theta, and finally for sigma r theta I have this. Alright, so these are my expressions. So sigma rr is equal to s cos square theta, sigma theta theta is equal to s sine square theta, and sigma r theta is equal to minus half of s sine 2 theta. And we remind ourselves very importantly again that this stress field that we have just obtained, so from this what we are obtaining, sigma rr is equal to s cos square theta sigma theta theta is equal to s sine square theta, and sigma r theta is equal to minus half of s sine 2 theta, minus half of s sine 2 theta. So these stress components, sigma rr, sigma theta theta, and sigma r theta that we have obtained, these pertain to the problem, the very simple problem that we would have if the hole were not present, but the hole actually is present. So we should be solving that problem and not this simple problem. So what can we do? So for that, a very classical way of proceeding is in this fashion. What we say is that, let's say this hole is very, very small. Okay, so our method of proceeding will work only if this the radius of this hole is much smaller compared to the dimensions of this rectangular plate. Okay, one might even say that we are considering an infinite plate, a plate of infinite dimensions, infinite of course relative to the dimensions of this circular hole. Now, because we have obtained this kind of a stress field, okay, this stress field will be true for around a circle. Okay, please note that we have obtained this field, these stress components for this rectangular plate, and still if we are considering the situation without the hole and we consider a circle, all right, so if we consider a circle like this, let me draw a circle, and because I'm imagining this circle, let me draw it in a dashed, with this dashed border. Okay, maybe I'll use the white color itself. And I will place it concentric with the original circular hole. Okay, so what I'm imagining is this kind of a circular border, this imaginary circular border, or just a circular just a circle whose radius is much larger than this actual hole radius. Okay, so from this diagram it may be a bit misleading, because the radius of this circle with the dashed border is certainly not much larger than this hole radius, but you imagine that such is the case. Okay, I don't want to be drawing this circular hole in the form of a little dot here. Okay, just to keep the picturization clearer. But what I'm going to say holds true only if this kind of this radius is much larger than this. Okay, so if this hole were not present, then all around the periphery of this dashed circle, the very same stress fields would be very much true. All right, so we need not consider anymore this original rectangular plate problem. Rather, we can consider just this kind of a circle. Okay, so if we just forget about this rectangular plate, it doesn't do us any harm, because if we are still considering this circle with the dashed border, the sigma RR, sigma theta theta, and sigma R theta is very much true. So if we so remember that we are still not considering the hole here. So if we sit at any point here, we can sit any point here, we can still very much obtain those stress components. It is absolutely no problem. Now we have to ultimately bring back this circular hole. So how do we do that? Okay, so in order to do that, the problem that we need to solve is actually this kind of a circle with the hole inside it, and now it is starting to look somewhat familiar to us from our previous solutions. Okay, so that's exactly what we are going to do in the next page. So we draw this circle again. We draw our imaginary circle like this. Let's make it reasonably big, and let us consider the real circular hole present inside it. So please accept the fact that these two circles are actually concentric. Okay. So what I'm saying is that in order to solve my actual problem, what I'm doing here is to imagine this kind of a circular border with the known stress components around it, and now I want to solve the problem anywhere within this thing. Okay. Of course, at the end of it all, I have to be careful about the dimensions that I'm talking about, because that is embedded within my understanding of the problem. So what I need to do is something like this. What I need to do is to consider a radius for this outer for this circle. Let's say that this radius is B, and then the radius for this smaller hole, let that be A. Okay, so let that be A. Now, for now, I will not say anything about the relative magnitude of B or A, but ultimately what I have to do is to make this B tend to infinity. Okay, basically I want to make B much larger than A. So what I'm basically doing here is this. I'm trying to solve a problem where the boundary conditions are like this. So maybe I write here. Okay, so I'll write it here. I'll leave this space for something else. So the boundary conditions that I need to have for this problem. So sigma RR. Okay, sigma RR is equal to, if we go back to the previous page, you'll see that this is S cos square theta. This is at R equal to B. Sigma R theta is equal to minus half S sine 2 theta, again at R equal to B. So we are writing basically the traction components in the radial direction and in the tangential direction. Okay, so when we are writing the sigma RR equal to sigma S cos square theta, we are actually writing the traction component in the radial direction. We are writing the boundary condition corresponding to the traction component in the tangential direction with this sigma R theta equal to minus half S sine 2 theta. Okay, please note that in the specification of these boundary conditions, I do not need to involve this sigma theta theta. It simply does not come about because the way the traction boundary conditions emerge. But I am not done with the specification of these boundary conditions because I now have to respect the presence of the hole. Okay, so this is the part. So let me write this clearly here, that I am actually bringing back my hole. Let me write that clearly here. And bring that down a little bit, and we are bringing back the hole. So sigma RR is equal to 0 at R equal to A. So on this inner periphery around this hole, please note that that is completely a traction free hole. So sigma RR equal to 0 at R equal to A. Furthermore, sigma R theta is equal to 0 at R equal to A. So our original problem will be said to have been solved if we can solve the elasticity problem corresponding to these boundary conditions, but only when we say that this B is much larger than A. So I repeat, what I have basically done till now is to reinterpret or re-represent the original problem, which was this plate with a circular hole, by this easier looking domain which consists of two concentric circles, but with the understanding that the radius, the outer radius here, must be much larger than this A. Only then this strategy will work. And this problem will be said to have been solved only when these boundary conditions, only when the elasticity problem with these boundary conditions are solved. Okay, so it boils down to this, that we have to choose an eddy stress function in such a way that the stresses emerging from those boundary from that eddy stress function will be satisfying these conditions. Okay, so the way ahead seems clean enough. Okay, so we have reduced the entire problem to a known kind of framework. Okay, so we have an elasticity problem, we have boundary conditions. All that you have to do is to select an appropriate stress function, and this is where we have to be a little bit clever in how we approach this problem. So you see, suppose uh, we had a situation that the sigma RR here, so you forget about the sigma R theta. Okay, let's consider the sigma RR. The sigma RR is present here in the form, this boundary condition is present in the form of a S cos square theta. But suppose it wasn't present in the form of an S cos square theta. Suppose it was in the form of some constant value. And if it were in the form of a constant value, and suppose you forget about the sigma R theta, then if you just look at the problem, sigma RR is equal to something constant, sigma R theta is not there, and sigma RR equal to 0 at R equal to A, then that is very much reminiscent. Okay, we don't have that, but I'm saying that if we had that, then that would be very much reminiscent of the pressure vessel kind of problem that we have already done earlier. Okay, so that was one of the earliest things that we did in the while addressing or demonstrating examples of the polar coordinate system elasticity problems. Okay, so we want to again rewrite this problem somehow in the form of something that we already know, and that we can actually do. If you think about it, what we can do is this sigma RR equal to S cos square theta. Okay, I will rewrite this thing. Okay, so there's a lot of rewriting and re-representations going on for this problem, and that's how we proceed. Always do things, always convert things in terms of what we know. So this s squared theta, that will convert, so this cos squared theta can be written as half of 1 plus cos 2 theta. Alright. Now you see, this is made up of two parts. One of them is this constant part, half of s. The other part, well, unfortunately, it is still dependent on theta. You can't do anything about it. Okay, but this gives us a clue. What if this original problem that we are doing, okay, where of course you understand when I say this original problem, I actually mean that this is basically a reworked version of the real original problem, which was the plate with a circular hole. So this is like the second hand original problem, and that second hand original problem I want to recast in maybe in a third hand original problem, if I can say that such a word. What I'll do is I'll extract this part, the half s part, okay, and I will write these boundary conditions as two sets of boundary conditions. Let me write that. Okay, so these boundary conditions I rewrite as two sets of boundary conditions. So what we are going to do ultimately in terms of the real implementation is to solve two different problems. So for the problem 1, so the problem 1 boundary conditions are like this. Sigma RR is equal to half of s, nothing else. Okay, we sacrifice this half s cos 2 theta. We don't really sacrifice it, but we sacrifice it for this problem 1, and we separate it out into a problem 2. So sigma RR equal to half s, sigma r theta, as you can imagine, we're going to set this equal to 0. And of course, this is at r equal to b. This also is at r equal to b. Sigma RR is equal to 0 at r equal to a. So that remains unchanged from this problem. And again, sigma r theta is equal to 0 at r equal to a. So that is my problem 1 boundary condition. For the problem 2, because you note that I must be having these two problems set up in such a fashion that when I club them together, I must get back these boundary conditions. So all that I have to do is adjust for the remaining terms. So half s is already taken care of. In order to get back this s cos square theta, all that I have to do is add to take care of this half of s cos 2 theta, and that is at r equal to b. Next, sigma theta theta is equal to sigma r theta is equal to, so that's where we write this term, minus half s sine 2 theta at r equal to b, and sigma rr is equal to 0 at r equal to a, sigma r theta is equal to 0 at r equal to a. So you see what we have done here overall. Okay, so this is a quick summary of what we have done. We started from this plate in a circular hole problem. First of all, we imagined that the hole is not present. We arrived at some notion of the stress field which is present far away from this hole. So okay, so far away from this hole means as if the hole is not present, and that can be represented, or that can be thought of to be the stress components present all around this kind of a circular boundary. And because we can think of it like that, we actually forget the original problem and recast it in this problem, in the form of this problem, where this is a large domain, large circular domain within which there is a concentric hole, and all over this boundary we have the same stress components present as the boundary conditions, the same stress components that we found on the first page as the boundary conditions here, and where we now respect that around the hole there is the traction free conditions given by this sigma rr equal to 0 and sigma r theta equal to 0. Now we would very much have liked to solve this problem directly, except that these boundary conditions are not very convenient. So we go an extra step and decompose this problem itself furthermore or once more into two problems. Problem 1 with these boundary conditions, so where the sigma rr is very much a constant, and this is almost like this is a ready-made thing for us already, because we know the pressure vessel problem solution. We just have to replicate that, and somewhat of a new problem where the sigma rr is having this kind of a form and the sigma r theta is having this kind of a form. All right, now the whole challenge of this problem ultimately boils down to finding a form of the Airy stress function which will actually give us this particular form of sigma rr and this particular form of sigma r theta. Okay, so how do we go about doing that? Well, for that a little experience is necessary, or you can go and try a little bit of trial and error, but it has been found already for us that if we take the form of phi, okay, let us call this phi 2, because let us reserve this phi 1 for this problem. The phi 2 will be for this problem, and that phi 2 form, it will be like gr cos 2 theta, where this gr is some function which is purely dependent on r, and that is multiplied by this cos 2 theta term. Okay, and you will find out that if we start out with this particular form, then sigma rr will come out in this fashion with a cos 2 theta dependence, and the sigma r theta will come out with a sin 2 theta dependence. Now what I really want you to do is to address this problem 1 and this problem 2, starting out with this form of phi 2. You already know what the form of phi 1 should be. To start out with this form of phi 2, find out the solution corresponding to this with these boundary conditions satisfied, club them together, ultimately what you get with this phi 1, and take the limit that b tends to infinity. Okay, so when you do that, all of these things in Jupyter Notebook, you will arrive at the final solution. So I think so this is like a combined lecture problem exercise for you. I will be providing the link to the entire solved problem with this phi 1 and phi 2 and the entire solution given, even with the limits of with the limit b tending to infinity taken. But I urge all of you to try this on your own. I mean, the amount of satisfaction that you will derive by doing this on your own is simply I mean, you have to feel that satisfaction of doing it yourself. Okay, but nevertheless, I will be providing the link to the solution in the description below. All right, so with this I end this lecture. Thank you very much.